Imagine you're spending the day on the beach. By afternoon, the wind picks up and a sea breeze blows onto the shore. Stay long enough into the night and you'll notice the breeze has flipped, flowing off the land toward the sea. But if you got on a sailboat and spent weeks on the ocean, you'd notice that the winds don't just shift with day and night. They follow vast, predictable patterns that stretch across the globe. In this video, we'll build on the last one by scaling up from local winds to thinking about the way air moves at a planetary scale through global circulation patterns. We'll talk about convection cells, prevailing winds, and zones of high and low pressure. Let's start by recalling the end of the last video when we talked about local winds like sea breezes. I showed you all this graphic demonstrating the convection cycle caused by uneven heating. The land heats up faster than the ocean and the air rises, which in turn causes a pressure difference. That pressure difference pulls the air out over the ocean, it cools and sinks back down to the surface, and then pressure pulls the air to land as a sea breeze. So pressure differentials cause air movement. And this is a really similar system to what happens at a much larger scale with global convection cells, these cycles of rising, flowing, and sinking. There are three major convection cells that move air around in the atmosphere. We're going to go in order of significance or strength, starting with Hadley cells. These are the primary or main driver of global air circulation. They are the strongest of the convection cells and can be found between the equator and 30 degrees latitude on both sides, north and south. Again, they are really similar to our local winds. If you remember back to when we studied the seasons, you may recall that the equator gets a lot of the most direct solar radiation from the sun. That causes this part of the Earth's surface to heat up, which means the air at the surface rises. Once it reaches the top of the troposphere, about 6 miles up, it starts to flow toward the poles. When the air aloft reaches about 20 to 30 degrees latitude, it starts to cool and descend. And once at the surface, it's pulled back to the equator. This horizontal flow to the equator is, of course, a wind. When we talk about convection cells at this scale, we're dealing with what are called prevailing winds, which means that they regularly blow in one direction. So here in a Hadley cell, we call the surface wind the trade winds, blowing from about 30 degrees latitude to the equator. The trades are the strongest and most consistent winds. You can see them on the globe here. They curve from east to west because the Earth is spinning underneath them. So it's kind of like they get a little bit left behind by the movement of the Earth. And this is called the Coriolis effect. The trades are so named because when ships were still powered by sails and wind, they carried trading ships west over the ocean. You can see here, for example, the trades over the Atlantic. The trade winds were central to early transatlantic trade as European merchants used them to move goods and to forcibly carry enslaved Africans to the Americas. Before we move on from the Hadley cells, let's talk a little bit more about pressure. Recall that rising and sinking air causes changes in pressure. Rising air leaves a low pressure zone at the surface of the Earth because there will be less air than before. Low pressure is often indicated on weather maps as a red L, so we can see that here on our globe diagram. The low pressure zone around the Earth's equator is called the intertropical convergence zone. It's intertropical because it's found in the tropics, which is the area between 23.5 degrees north and 23.5 degrees south. And the zone is convergent because the trade winds on either side are meeting. They are converging. And then on the other hand, sinking air causes a high pressure zone at the surface. This is indicated by blue H's on weather maps. So here at about 30 degrees latitude, sinking air piles up on the surface, giving us the subtropical high, so called because it is below the tropics, either north or south. This band is also called the horse latitudes. The wind is pretty slow here, and supposedly when ships were still powered by sails and wind, they could run out of supplies to feed their horses on long journeys, and so they would end up throwing the horses overboard. But to be honest, I don't know if this is just like a geography myth or not, but this is what I was taught, and it's what geographers continue to teach, but it seems kind of suspect, but at least it's memorable, right? Second in importance to the Hadley cells are the polar cells. These are convection cells above the north and south poles between about 60 degrees and 90 degrees. Because the poles generally get the least direct sunlight, the air here gets quite cold and sinks, causing a high pressure zone on the surface at the pole. And because air moves away from high pressure zones, it heads toward the equator. So we call these the polar easterlies because they move from the east and point toward the west. So at this point, you may ask yourself, if the polar region isn't getting much heat from the sun, what's making this air rise around the 60th degree of latitude? Well, once we cover our third and final cell, this will start to make a little more sense. So the last convection cell is called the Ferrel cell. This is the weakest and least significant of the three and can be found between the 30th and 60th degree of latitude. It's considered a secondary cell because it doesn't have the strong heating like the Hadley or the strong sinking like the polar. It does have a prevailing wind moving toward the poles called the prevailing westerlies because they come from the west. So back when ships were powered by sails, this was how they would move back to the east, carrying goods, gold, and silver to Europe. But the Ferrel cell is actually so weak that the westerlies often get disrupted by storms. So that makes the Ferrel cell not really that useful of a model because the wind doesn't always follow this pattern. Okay, now for the lifting mechanism behind both the polar cells and the Ferrel cells. When two air masses of different temperatures run into each other, we call this a weather front. So when the cold polar air meets the warmer air from the Ferrel cell, we call that the polar front. It looks like this with the cold polar air in blue forming a sort of wedge shape, and then the warmer air of the Ferrel cell in red. What's happening here is that this colder air is forming a sort of barrier because the air is dense in terms of the molecules being packed in from sinking. The warmer, less dense air starts to rise over it, leaving a low pressure zone behind. And the convergence also forces some of that cold air to rise too, sending it back poleward to complete the polar convection cell. But much of the cold air gets caught up in storms at the polar front and moves laterally near the surface, neither toward the equator nor toward the pole. It moves along the front as a storm system. One thing to note here is that this three-cell model featuring the Hadley, Ferrel, and polar cells is just that. It's a model. It's an idealized way of thinking about the Earth's atmosphere, because it makes it easier to understand and learn. But it doesn't account for a lot of other differences found at the Earth's surface, like the differences in heating between land and water. It doesn't account for mountain ranges, and so on. In reality, the atmospheric circulation on Earth is more lumpy. So this is a map showing a more realistic pattern of circulation, specifically for the month of July. As you'll recall from the seasons video, the amount of sunlight hitting different parts of the Earth's surface changes throughout the year. So we see here these little red arrows indicating that more realistic flow of wind. It doesn't look quite like the simple trade winds, westerlies, or easterlies from the model, right? We can also see that pressure doesn't form straight, even bands. Highs often form over the oceans because air tends to cool and sink here, similar to our discussion of sea breezes, except it's not really affected by day and night on this global scale. We can see these oceanic highs in both hemispheres, north and south. During the summer, lows tend to form over land, where air warms and rises. We can see this especially over mountain ranges in low and mid latitudes, so nearer to the equator than the poles, because they get a lot of direct sunlight. So since this is a map for July, we can see the lows in the northern hemisphere, where it's summer and getting more direct sunlight. We also see the intertropical convergence zone, that band that's supposed to be over the equator, will move with the change of seasons. Because the low pressure here is primarily caused by airlift from heating, the line follows the parts of the surface getting the most direct sunlight. So during our summer in the northern hemisphere, the zone moves north, and during our winter, it moves south. And this is just to give the basics, to give you an idea of how atmospheric circulation works more realistically. You won't be asked to memorize this map, of course, but rather I want you to remember that it isn't just the smooth 3-cell model. As you may have noticed while doing your Project 1 assignment, the atmosphere is not always easy to see. We tend to experience the atmosphere more through physical sensation, especially wind. But while we cannot always see the atmosphere, we do experience it in a very significant way when we breathe. When we draw air into our bodies, we incorporate it into ourselves. So for better or worse, the atmosphere and whatever is in it becomes a part of us. So for your third selfie field trip, we'll be taking pictures of places or spaces where we breathe. We'll take 2 pictures, one where it's easy to breathe and then one where it's difficult to breathe. And as always, share your pictures in the forum, answer the questions, and then reply to 2 or more peers. And by the way, I'm slowly making my way through the map project posts, and hopefully I'll be done grading them by the time you're watching this. Our next video will be in Module 4, where we'll be covering the hydrosphere, or the water found on Earth and in the atmosphere. In Module 4, we'll talk about the water cycle, which covers how water moves from the surface to the air and back. And then we'll talk about surface and groundwater and a bit about weather. Thanks for watching. See you next time.